This video describes the design and basic operation of Klystrons. Why are vacuum tubes still used in high-frequency technology? Even the most advanced semiconductor technology struggles to generate very high pulse power. While longer pulse durations and intra-pulse modulation can work in most cases, high accuracy is crucial in applications like weather radar. In these situations, transmitting extremely short pulses requires an exceptionally high pulse power of about 500 kilowatts to achieve sufficient radar range. For more cost-effective solutions, non-coherent transmitters often utilize magnetrons. In contrast, transmitters that need precise phase coherence typically use traveling wavetubes or Klystrons. The electron gun is the radiation source in cathode ray tubes. The electron gun provides a narrow, collimated electron beam with precise kinetic energy. The core of the electron gun is the cathode. This is usually a cylindrical body whose surface is covered with barium oxide for better electron emission. The cathode is charged up to several 100 kV. In Klystrons, this voltage is referred to as the beam voltage. The cathode is heated by a filament to a temperature of about 1300 degrees Celsius. This heat causes free electrons to be released, creating a cloud around the cathode. The quality of the vacuum within the tube affects the distance these electrons can travel. A better vacuum allows the electrons to move farther away from the cathode. The Wennet cylinder serves as a control electrode for focusing the electron beam. It was developed by the German physicist Arthur Wennet in 1902–1903. This cylindrical device carries a slightly more negative electrical potential than the cathode. By adjusting this voltage, the number of electrons that can overcome the potential barrier is altered, which can change the intensity of the electron beam. The Wennet cylinder has a hole in the direction of the anode through which the electrons can leave the electron gun. A very high anode voltage generates a strong electrical field that attracts the electrons and causes them to migrate in the direction of the anode. To achieve a faster electron speed, the distant anode must be set at an extremely high voltage. To address this, an additional pierced anode is introduced. The electric field created by this anode accelerates the electrons effectively, even at lower anode voltages. While some electrons are indeed captured by the anode, the majority, due to their significantly increased speed, pass through the hole in the anode. The blue arrows indicate the direction of the Coulomb force generated by the electric field. Consequently, the motion of an electron occurs in the direction opposite to that of the arrows, toward the source of this force. A cavity resonator is now inserted, with the electron beam passing through the center hole. As long as this cavity resonator is without additional voltages, the electrons remain unaffected. This resonator is called the buncher cavity. These cavity resonators make the Klystrons highly frequency dependent. Klystrons are typically designed to operate at a single fixed frequency. The bandwidth is usually only 0.1 to 2% maximum. For Klystrons in S-band, at 2.7 to 2.8 GHz, this corresponds to a bandwidth of only about 55 MHz. An oscillation in the cavity resonator additionally influences the electron velocity. They are accelerated by the more negative potential and decelerated by the more positive potential. This results in a so-called velocity modulation of the electrons. Faster electrons catch up with slower electrons and form tightly confined electron bunches with them. Remember the name buncher cavity. There are only a few electrons in between. These are the electrons that passed through the resonator at exactly the point in time when the oscillation was at its 0 point. A strong permanent magnetic field keeps tightly packed electrons in bundles from repelling each other and scattering, which helps maintain a sharply focused electron beam. The electron bunches created by the velocity modulation now fly through a second resonant cavity. The second resonator with its output coupling is called the catcher cavity. When the electron bunch passes the first wall of the cavity, the free electrons in the wall material are displaced and migrate to the opposite side of the cavity. But the electron bunch quickly arrives on the other side as well and sends the electrons back again. This creates the output oscillation in the resonator. Provided that both resonators are constructed the same and the mean velocity of the electrons is constant, then the frequency of the output oscillation is the same as at the input of the tube. A two-cavity klystron achieves a power amplification of about 20 to 30 decibels. The cavity gets the energy for this oscillation from the kinetic energy of the passing electrons, which are slowed down by it. The efficiency can reach up to 40%. This efficiency is calculated from the ratio of the power supplied to the klystron as a DC voltage power supply and the radio frequency power output. Nevertheless, these electrons still have enough energy behind the amplifier resonator, so the collector that catches them must be well cooled. This cooling can be done either by a forced airstream or by a cooling liquid. The two-cavity klystron is an amplifier tube used primarily in military radar sets. This klystron, an NSN 662, is British-made and liquid-cooled. The resonant cavities also need to be cooled. Strong currents flow in their walls and their ohms resistance causes them to heat up. The input and output of this klystron are configured as waveguide connectors. At the input, an adapter with an N-type socket for coaxial cable is screwed on. The mechanical size is determined by the size of the cavity resonators. This klystron is most likely designed for a frequency in the C-band. The diameter of the resonators would then be half of lambda, so a little less than 3 centimeters. Space must also be found in the housing for the coaxial permanent magnets. The output is equipped with a ferrite circulator device configured as an isolator to prevent reflected radio frequency from flowing back into the klystron in the event of a mismatch, which could potentially destroy it. The average output power of klystrons can be as high as 500 kilowatts and the pulsed power can be as high as 30 megawatts at a frequency of 10 gigahertz. Power amplification of up to 30 decibels is achieved. The power amplification of a two-cavity klystron can be improved by adding further cavity resonators. This results in a multi-cavity klystron. The additional cavity resonators are called amplification resonators. With such klystrons, power amplifications of 30 to 60 decibels can be achieved, which corresponds to amplification factors of 1,000 to 1,000,000. Thus, the efficiency can also be significantly improved. Losses still occur due to the non-ideal focusing of the electron density and the remaining energy of the electrons, which is converted into heat in the collector. Multi-cavity klystrons can be used to increase either the gain or the bandwidth of the tube. To increase the bandwidth, they are often operated with slightly detuned cavity resonators. This reduces the overall gain, but a significantly larger bandwidth of up to 8% is achieved. In a klystron, DC voltages are converted into an RF-AC voltage using electrons. The energy they transfer is kinetic energy whose size depends on the high voltage with which they are accelerated. The maximum output power is proportional to the cathode voltage applied to the anodes, and the number of electrons in the beam. The disadvantage is that higher voltage increases the probability of breakdown. However, the number of electrons in an electron beam is limited. It can be increased by using multiple electron guns. This leads to the designation of multi-beam klystron. A multi-beam klystron, abbreviated MBK, is, to put it simply, several single-beam klystrons connected in parallel. Their resonators, except for the input and output, which must be common, and their focusing systems, for example, magnetic field, can be either common or separate. Compared to a single beam klystron, the high voltage can now take on much lower values or the output power can be multiplied. Focusing the electron beams is difficult, but can be achieved, for example, by using solenoids through which direct current flows around each electron beam. The problem is that the individual electron beams must be as close together as possible to be guided through a common cavity resonator. The strength of fields is often represented using color gradients, where red indicates a maximum strength and blue signifies a minimum. However, in this context, blue represents a negative maximum. To ensure that the maximum strength of the electric field effectively interacts with the electron beams, the resonator is operated at its first harmonic wave. This choice also increases the size of the resonator, as its diameter becomes one whole wavelength instead of half a wavelength. The 4-beam klystron depicted here is infrequently used. In practice, a significantly larger number of electron beams is typically employed. Higher modes are also possible, as are other resonator shapes, such as a coaxial form. These types of multi-beam klystrons, with a pulse power of up to over 100 megawatts, are used primarily in research for particle accelerators. Frequencies from the UHF band to the L band are required there. This makes the klystrons 2 to 3 meters long. The dimensions of the resonators also set an upper frequency limit. Klystrons with classic cavity resonators can be manufactured for frequencies up to 35 GHz. A high-efficiency long-pulse multiple-beam klystron, designated the VKL8301, is being developed by Communications and Power Industries LLC for the DESY Terra Electron Volt Superconducting Linear Accelerator, abbreviated to Tesla, in Hamburg, Germany, an international X-ray laser research facility. This device uses 6 electron beams arranged in a larger pitch circle positioned off-axis. These beams interact with a combination of higher-order modes within a conventional klystron cavity, allowing for the efficient generation of high-power RF signals. At much higher frequencies, however, the cavity resonators become too small. In a planar sheet beam klystron, the resonator structures can be milled into a block of copper alloy. The electron beam in the klystron is designed to be very flat and wide, thanks to a specially shaped cathode. It is maintained in this flat configuration by a magnet system. The klystron is manufactured by milling 2 mirror image halves, which are then stacked on top of each other for assembly. Simultaneously, pipes for coolant can be integrated into the solid block during this process. This technology allows for the creation of klystrons with cutoff frequencies exceeding 90 GHz. The high precision required for the cavity resonators, ranging from 2 to 3 micrometers, necessitates using of new manufacturing techniques typically found in the semiconductor industry. This process is known as LIGA, which stands for lithography and electroplating, in German language galvanic, and is a form of photolithography. The klystrons described so far are primarily amplifier tubes. While they can also function as oscillators with appropriate feedback, this is a complex procedure. It necessitates the connection of a high-quality frequency-determining component outside the tube. Additionally, broad tuning is generally not feasible, as each cavity resonator would need to be retuned individually. In contrast, a repeller klystron is a self-oscillating tube with only one resonant cavity, which can be tunable. However, only very low RF power can be generated with a repeller klystron. The electron beam is generated in the same way as in the two-cavity klystron, and the same applies to the velocity and density modulation. The anode is in the form of a grid, but it accelerates the electrons in the same way as a whole anode in a two-cavity klystron. The resonant cavity is an external circuit. Only a small part of the cavity walls, with the holes for passing the electrons, is integrated into the tube. The feedback necessary for undamped oscillation is provided by sending the electron bunches created by the velocity modulation back to the resonant cavity through the negative reflector plate, where they release their energy back into the resonant cavity. This negatively biased reflector plate is called a repeller. That's where this tube got its name. The limitation of the output power is that the electrons hit the cavity resonator and heat it considerably. At low power levels, this heat can still be easily dissipated. Larger power levels would destroy the cavity resonator. In the past, repeller klystrons were used as local oscillators in receivers up to the Ka band. Today, these frequency ranges can be served by semiconductor devices. Klystrons have a wide range of applications in physics and high-frequency technology since the power levels achievable with klystrons cannot be attained with semiconductor components. This is why the high failure probability of vacuum tubes is tolerated. Older military radar sets sometimes still use klystrons as high-power amplifiers. Klystrons are used where the use of intra-pulse modulated transmitters is problematic. These are mainly weather radar sets. Klystrons are used in particle accelerators in research. Elementary particles can be accelerated using high-frequency fields. However, this requires huge RF power in the order of 250 klystrons, each operating in the megawatt range. These klystrons operate in the frequency range from about 200 MHz, which requires quite large resonators, up to the S and X band. Larger multi-chamber klystrons are used in the transmitters of terrestrial television stations in the UHF range. Applications of klystrons in the W-band are currently the subject of laboratory research. I hope you enjoyed the video. Thank you for your attention.